the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through the dimensions of a vector space. The concept of dimension, the subspaces of finite dimensional vector spaces, all that fun stuff. And now we're heading into the basis theorem. The proof of this theorem can be found in any linear algebra textbook, so I'm gonna kind of skip it for now just to save time so I can get the recording finished. So what is the basis theorem? Well, let V be a p-dimensional vector space, where p is greater than or equal to 1. So we have a vector space that has a basis consisting of p vectors. And remember, once you have a basis for a space, then all bases for that space will have the same number of vectors. So if your vector space is 10-dimensional, then any basis you grab from that vector space will have 10 vectors. So with that being said, you have a finite dimensional vector space with dimension greater than or equal to 1. Any linearly independent set of exactly p elements in V is automatically a basis for V. Now this should not, hopefully, blow your mind. I have a p-dimensional vector space, and by the way, I have p linearly independent vectors from that p-dimensional vector space. Well, if it's p-dimensional, that means any basis must have p linearly independent vectors. So far, I have p of them already. If you add any more, well, that set will become linearly dependent. By the way, the second half just says any set of exactly p elements that spans V is automatically a basis for V. This is really just hammering down the fact that if you have a 10-dimensional space, you need 10 vectors that are linearly independent that span that space. If you have 10 linearly independent vectors from that space and it's 10-dimensional, then you have a basis. So I don't really need to define this honestly, but Hermite polynomials are orthogonal polynomials. It's a whole sequence of orthogonal polynomials. You don't need to know what that means yet, but we might delve into that in linear algebra. But it suffices to say that the first four Hermite polynomials are 1, 2t, negative 2 plus 4t squared, and negative 12t plus 8t cubed. By the way, there are actually two different definitions for Hermite polynomials, so this is going to be the physicist's definition. There's also one for probabilists, but we're not going to use that one. Show that these polynomials form a basis of P3. Now, it really helps to remember that P3 actually is a 4-dimensional vector space. We would say that 1, t, t squared, and t cubed form the standard basis for this space. For vectors, the dimension of P sub 3 is 4. However, let's not assume that here. Let's just see what happens. We're going to build a change of coordinates matrix using these polynomials right here. The first basis vector, we're going to call 1, 0, 0, 0. This second basis vector, we're going to use the vector in R4, which is 0, 2, 0, 0. This third vector will create a B coordinate vector here, which is negative 2, 0, 4, 0. And finally, this last vector, again, its B coordinate vector will be 0, negative 12, 0, and 8. Note that this change of coordinates matrix has 4 pivots, which implies by the invertible matrix theorem that the inverse of our change of coordinates matrix exists, which implies, again by the invertible matrix theorem, that our columns of our change of coordinates matrix are linearly independent. And remember, these columns are the coordinate vectors for our original Hermite polynomials, which implies that those original Hermite polynomials are linearly independent. Now, what does this have to do with the previous theorem? Well, we do know that P sub 3 is a 4-dimensional space, just because we know a standard basis for this. And from this theorem here, theorem 12, any linearly independent set of exactly 4 elements in our vector space p sub 3 is automatically a basis for p sub 3, as long as p sub 3 is a 4-dimensional vector space, which it is. Since the dimension of p sub 3 is 4 and we have 4 linearly independent vectors from p sub 3, that set 1, 2t, negative 2 plus 4t squared, and negative 12t plus 8t cubed must be a basis for p sub 3 by the basis theorem. Very nice, clean way to show that you have a basis for a space. As long as you know those vectors are linearly independent and it matches the dimension of the space, you have a basis for the space. So that pretty much does it for this video. I know it's somewhat short just because we skipped the proof on it, but again, I'm trying to squeeze in a lot of video recording this semester, so I certainly hope that you can crack open your textbook and read through the proof of the basis theorem. All right, I hope to see you in future videos. Have a wonderful day. Be wonderful human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.